There's a lot of you here. That's wonderful. I'm going to try to talk most of you out of dropping this class today because I want to make sure that everybody actually wants to be here. It's a real drag for me to try to teach people who aren't really interested in what we're doing here. And so, having just gotten all the course evaluations back from last semester, there seems to be one complaint for this class and a lot of praise, but I want to focus on the complaint because I want to make sure that you guys, have a chance to take something else if it's more exciting. And that complaint, and really what at the heart of this class is that it's mostly a lecture class. So I'm going to stand here and talk to you guys for an hour and 20 minutes every class twice a week. So if that doesn't sound fun to you, listening to a guy talk about the stars for dozens of hours, you should probably drop this class right now. Because, it's just that's the way this course is set up. That's my job. That's what we're doing here. So it's going to be fun, though, because it's not going to be just your average PBS Nova special about the stars. We're going to be really crushing into the bleeding edge of what's known about not only our star, but all of the stars, and we're going to try to build towards a bigger picture of the cosmology. So I'm going to introduce myself today. I'm going to talk a bit more about the course in detail, and then we'll probably, depending on how much time we have, we'll get into a little bit of the content. In order to talk about the stars, the best example we have is our own sun. So we'll start there, and we're going to do that for a number of classes because it's the star we know the most about. And that doesn't mean we know everything about it. So there's actually quite a few mysteries that are being discussed in the professional world right now. Some really exciting controversies. But this goal of this class is to eventually work our way towards a bigger picture of the universe as a whole. So we're going to, once we get a bit of understanding about the stars under our belt, we're going to talk about galaxies. We're going to move out. Eventually, we're going to talk about this whole universe, and we're going to work towards something called a cosmology, right? And cosmology is a really funny term because it's an ancient word. It goes, I would say all peoples and all cultures going back as far as we have records of have cosmologies. And a cosmology is really just people, us, trying to make sense of our place in the universe. Now, cosmology becoming a hard science, like being part of the physics department, that's a really, really new thing. So nobody would have considered cosmology a science until about the 1960s, and really seriously until the 70s or even 80s. And that's because of some interesting developments concerning this theory called the Big Bang. And the Big Bang is actually on the ropes right now. So it was a very popular theory for most of my life and a good part of the 20th century. But there's a fair amount of dissent concerning observations that we're getting back from our latest space telescope, which is called the James Webb. And so we're going to work towards all of that. But we have to start here in our solar system with our star. Now, last semester, for those of you who are here, we did our solar system in depth. We looked at all the planets, all the moons, more moons, and we made sense of this place and tried to come up with a good formation story, although, jury's still out. It's very difficult to make sense of something that happened billions and billions of years ago. So we won't have time for that. And if you're interested in that and you want to, we can do that in the fall. We'll have that class again. But this class is going to be fixated on things bigger. And so we start with the stars. So I want to go over the course, the syllabus, the assignments with you guys and make sure that isn't intimidating any of you or just doesn't sound fun. I mean, there's too many courses on your catalog for you to take a class that doesn't really seem interesting to you. So please, do some deep contemplation today when you go home and think about whether you really want to take this class or not. Because it's just so much more fun for me if people are into it. And a lot of people are, because I think it's a pretty exciting topic. I mean, for most of human history, folks were, the sky was everybody's Instagram. It was everybody's Netflix, right? That's all we had at night. There was a campfire, and people were telling stories with these stars. And so we should probably all, as a people, have some understanding of what's going on up there and what this means. And it means something very different to modern scientists than it meant to most of humans throughout all of our distant ancestral evolution, right? And I'm going to try to bring that in as much as possible. And I have some different reference textbooks. And I really want to examine the way that people have thought about it across time. Because if you think about it, we've been treating the stars as material objects for, gosh, a few hundred years, basically. And human evolution may stretch, let's say, behaviorally modern humans with language and stories and so forth may go back generously 500,000 years, right? So that's a long time, right? This is like a tiny slice of the pie that we've even had this approach to thinking about the stars. So, and I don't think that those people were idiots. I don't think the stories they told were just superstitious entertainment. I think they contained a lot of wisdom. So we're going to be bringing in a lot of that mythology where possible, because ultimately, in trying to generate a cosmology, which is kind of the goal of this course by the end of it, it's very difficult to take our own human experiences out of any stories that we tell. And I would say that the story is the fundamental unit of knowledge. It's the fundamental way that we transmit knowledge to one another, to ourselves, right? You wake up in the morning and you're like, what do I have to do today? And you set it out, and it has an arc to it. And all of our lives are like that. And so it's very difficult for us to not tell stories about the sky that are similar to our own experiences. And I think that that's kind of where we're at today in some sense. We try to be very objective about it, but at the end of the day, we see things as human beings because we all have births and deaths, and so we're looking for that in the universe as well. And whether that's a reasonable approach or not is up for grabs, and we can discuss all sides of that matter as we get closer. So, more on that in a minute. So we'll do the syllabus, we'll do the course. I'm going to introduce myself, tell you a little bit about who I am really quickly. And then with what time remains, we'll think about light a little bit, because of course, this may or may not have occurred to you, but unlike every other science in the world that I can think of, we can't do experiments on stars, right? We can't just put them in a test tube in a laboratory and control them and have different conditions, right? All we have is light. And so it may surprise you to find out that light is actually a somewhat vaguely understood phenomenon to begin with, right? We have fantastic mathematical descriptions of how light behaves, but in terms of understanding what the atoms are really doing to one another in order to affect light, that's a whole different matter. And so if we're trying to use all of this light to make these pictures up about what the stars are made of, how they're behaving, and we only have a hazy idea of what light itself is, then our mediator, right, our readout is going to be a little less reliable. So I'm going to crack open the idea of light a little bit today, but it's going to be something we keep coming back to, because everything we know, even about our own sun, right, comes down to interpreting the signals of light and breaking them apart into their different colors. And when I say light, by the way, for the rest of this course, I don't just mean like visible light. I mean radio waves and gamma rays, right? These are all these forms of radiation are light, truly. So we'll do that. We're going to start picking out the solar structure, and then we're going to start talking about magnetism, because the sun has a really incredible magnetic, cycle, right? It has a system of cycles. And those cycles are becoming really important in understanding how our own Earth behaves too, which is really, really fascinating. In terms of actually controlling, things as important as climate and weather systems, right? Maybe even seismicity, earthquakes, tectonics, things like this could be involved in the sun's presence, right? So we have to understand magnetism just like we have to understand light. We need to make some sense of what magnets are, because again, magnetism is one of those things like light, where we have fantastic equations to describe how magnets behave. But if you go and ask your favorite physics professor how a magnet works, it's going to devolve very quickly into a series of equations. And so I want to try to give you guys some sort of picture of how to think about what the atoms are doing to affect magnetism, so that then we can turn that back on the sun and actually understand why in the world something so far away as the sun might be having such an influence here on Earth. And then at the beginning of next class, hopefully we can get into space weather a little bit, solar wind, and so forth. So that's the plan for today. We'll see how far we can get. I think I've kind of outlined the main gist of this course. The goal is both to examine the extant knowledge that we have about the stars and about cosmology, right? This is the stuff you're going to find in your textbook. And I guess it's as good a time as ever to mention that the textbook is online. It's free. Hopefully everybody has access to Moodle. Has everybody had a chance to check out the page yet? Anybody having issues with that? You made it in? All right, let me know. Okay, so Moodle is a really interesting format. Love or hate it. All of your assignments, all the reading every week's going to appear up there. I'm trying to publish it, at the beginning of the week. You should be able to access, what part of the textbook we're going to be covering. Now, previously, when I've taught this class, so I've tried to make attendance a reasonable portion of this class, because I think that being a lecture class, it's kind of pointless if you don't come, because then we can't interact. And you can't actually, I'm going to try to bring something into this course that isn't in the textbook. So what I started off this rant was, we're going to look at the standard body of knowledge, but we're also going to try to push that knowledge and push on it and see where it breaks and see where the future of our understanding might lie, because I think that's what science is really all about. There was some really disastrous memes going around in the last couple of years about trust the science, right? And that's a cool idea if it means trusting the process of coming up with new ideas. But it's a really oppressive, disastrous situation if it comes down to believing in some theory, right? Because the minute that you believe in your own theory, you have no room to grow. You have no room to continually understand the system. And so what we're going to do in this class and why coming to this lecture matters so much is because I'm going to try to spend more time here talking about the things we don't know, whereas your textbook, the reading quizzes over your textbook, and a lot of the watch material is going to concern the extant body of knowledge, so the things that people have cataloged over the last few hundred, maybe 1,000 years, the things we think we know, right? It's easy to write those down and read those in a textbook, but we're less willing to put the things we don't know into the textbook, and so that makes this conversation we're having here really important. So to that end, what I've done previously, is I've passed an attendance sheet around. But that was kind of a drag for me and for everybody, honestly, because, it's difficult to keep track of. You have to sign in, and it just feels very childish in some sense. So I want to change that up this semester. Here's what's going to happen. The attendance is worth a pretty serious part of your grade. If you don't attend this class, it's going to kick your grade down probably at least one letter grade. So how are you going to get attendance points? It's going to work like this. At the beginning of each class, before we start into the new material, I am going to call on you. I'm going to call on you completely randomly. I'm going to have a little sheet up here, and if you're not here, I'm going to give you an X. If you're here, I'm going to give you a check mark, whatever, right? And so what I'm going to do, I don't expect you to wow me or blow my mind or anything, but I do expect you to have thought a little bit about the last week's course material, right? I want you to think about the lecture a little bit. I want you to think about the reading material. I basically want to make sure the lights are on upstairs, right? I want to make sure that you're actually with me on this. And that's it. And honestly, if you have questions as we go through these lectures, please raise your hand in the middle. I would much prefer to be having a dialogue with you and see what's interesting to you. If I'm going through some topic and I say something and it doesn't make sense to you, raise your hand. Ask stupid questions. This is a great skill to learn early in life while you're still young, right? And I don't mean stupid because you haven't, read the assignment or something, right? I mean stupid because something doesn't make sense. If it doesn't make sense to you, it doesn't make sense to 20 other people in here, I guarantee you. So ask questions, participate in this class, right? And the best way I can evaluate that is really just a random sampling because I don't know, it just seems more productive. And I would like to develop this into more of a conversation as possible. Okay. Questions about that? All right, so if you do miss a class, you have to miss a class, you have a doctor's appointment, you're not feeling well, you partied too hard last night, don't email me about it, please. Don't tell me that you're sitting on the toilet, and I don't want to hear about this, okay? Please. Do this. If you want attendance, if you're worried that maybe you missed your attendance points, I put all of these lectures, I'm recording them right now, I put them on YouTube. There's a link to that in your syllabus. Watch the lecture. Send me a little paragraph, send me an email with some thoughtful insight about the lecture. Tell me something that was interesting to you, that you want to know more about, that something that you hated. I don't care. Just, again, let me know the lights are on upstairs, and I'll mark you down for attendance for that class. All right. What else? So you do have to kind of execute on your own deadlines in this class. So I leave all the quizzes open all semester. I'm going to close them out before finals week. So if you really don't want to do the quizzes until the very end of the class, it's completely on you. You guys have to, a lot of you, are well grown up already, but most of you are going to have to figure this out at some point. So, get those done. The video assignments, on the other hand, are a little bit of a different story. So every week, you're going to have a short little quiz over the reading, and you're also going to have a video response. They're like 2-minute responses that you do on Flipgrid. They're really easy. I ask you to go through usually something on the watch list. I think this first week, we're just introducing ourselves to each other. You have to put a little 2-minute video up. You need to do that by Saturday night, okay? Or Sunday morning is fine. I'm not going to be grading them super early or anything. If you don't turn it in, I'm not going to get notifications if you turn it in late. So you have to send me an email with a link to it if you want credit for it when it's late. I'm also going to penalize you for turning it in late because I don't really like having to grade them all separately. So it's kind of painful for me. So please, turn your video assignments in on the weekend. Do the quizzes every week. It'll be easier for you to keep up. If you don't, that's on you. Now, how many of you are taking the workshop? A fair amount of you? Okay, all of you, great. Workshop is pretty simple too, although I think it's super valuable. And there's going to be a short little quiz over there. It shouldn't take you more than 20 minutes or so every week. But the workshop's kind of incredible. It's this online software, essentially, where you can go in. It costs $30. You need to buy it. You go in, and you can basically explore the known universe. You can zoom in. You can explore different star systems. And the workshop will lead you through different exercises to get you acquainted with this. But it's really cool. You can go back in time. You can see where the stars were from different perspectives. You can go back to your birthday and see where the stars were in the sky. You can go way into the future. It's a pretty cool tool, and I think that it'll really help solidify the content that we're doing in the lecture side of things too. So those are due every week too. So altogether, if you're doing the workshop, you got a quiz for that every week. You got a quiz over the reading, and you have a 2-minute video response. And that's it from week to week. It's not that much stuff. Yes? Nope. Next year you do, though, I think. We're reformatting this for the GE college. Yep.
Is it the same, a specific link to the Starry Night as last time?
Yep. Make sure it works for you and your subscription's still going. Yep. Any other questions over that? Yeah. You know what? I think at least at one point you will have the option of doing that instead of a new response. But if you want to, I think that would be really healthy. I'd appreciate it. I think they're fun to check out what other people are up to and their responses. So, and without me saying anything, people usually do. So it's as close as we get to social interactions here. So actually, along those lines, I've tried something in the past. Sometimes it works out, sometimes it doesn't. I'm going to try it again this year. I really like to, once a week, I like to show up early, have people come early. If you want to come at like 8 a.m. on Thursdays, I'm going to make some coffee. You can bring a cup. We can hang out. You can get to know your classmates a little bit if you want to. Usually it ends up being like a core nucleus of people who come to these things, if at all. So let's try that. We'll start it next week. Let's not worry about it this week. But I think we're in for some sort of winter storm, actually. So we might not even have class Thursday. I don't know. We'll see. But I do like to do that, and I'll remind you guys about it next week when we try that out, because it's fun. I like to find out who you guys are, what you're studying, and I think it's fun for you guys to get to meet each other a little bit more too. So yeah, you can interact as much as you have energy for on the Flipgrids too. But the first assignment will be introducing yourself. I think the second assignment is going to be responding to somebody else's introduction, if I recall correctly. Okay. So let's see. And then the other big component of your grade for this class is going to be the project. So there's the final project. It's not that big of a deal, honestly. It's basically an extended version of one of these video responses. It's a bit longer. I'm going to ask you to kind of go a little bit more in depth into some source material, get some other references to bring in. You're basically making a short presentation and delivering it in video format. So nothing to sweat, and we'll talk more about that as we get close to it. There's also the option, if things are sort of flagging for you, if you're not really pulling together if your points aren't appearing the way you like them, you can do a creativity project. This is basically anything you want, right? It's something related to the material, something star-like, but you can do a poem, you can do a short story, you can do a painting, whatever you like. So, by the way, this is the YouTube site where you can get the lectures in the future. All right. By the way, if something doesn't appear on Moodle, please let me know. All right, so who am I? So I'm primarily an artist and a scientist as well. This is actually just a small part of what I do. I play music. In grad school, I worked on these evaporation machines quite a bit. I did my PhD at Columbia in New York City, and I started teaching there. I've taught at University of Portland, Rivier in New Hampshire, and now I'm here. You know, my background's in material science, and so a lot of the way that I look at things is in terms of their material structure, and that's going to become really important as we start talking about the stars, because I think a lot of the way we've learned to think about the stars is very mathematical in nature. I've also got this podcast too. This is a huge part of my life. I do this with my wife. She's a professor in the biology department. If you guys are interested, check it out. I'll be bringing this in more and more into the class as we go forward, because I've talked to a lot of important astronomers and cosmologists over the years. And this is actually, I think this is in some sense what makes this a very rich lecture series, because I have a chance periodically to really interact with people who are working at the front of a lot of this knowledge. And so we'll see more and more and more of that. I'm also working on a book right now with my wife, where we're trying to actually give some sort of material form to the atom. It's kind of, you probably think that things are made out of atoms, and fair enough, but I don't know how many of you have taken basic biology, chemistry, physics, but very quickly when you start studying the atom, it turns into a sea of math once again. Now, math is really useful for telling us what's happening, but the idea that things are made out of math is a little bit preposterous, and so what we're trying to do is give some form to that, and that's going to crop up more and more as we go forward, especially when we talk about light and when we talk about magnetism and electricity, which play heavily into the function of the stars. So I won't belabor that point, but it will crop up over and over and over again. All right. Well, let's check out the sun. So the consensus story of the sun is that it's a giant ball of gaseous plasma, which is sort of compressed under its own weight. And this is powering these fusion reactions at the core, and that the light is essentially being generated at the core and relayed out to the surface and eventually makes its way to us. we'll start to pick apart, especially next class, how we arrived at this model, because it's an interesting model that was developed in the 1800s for the most part. And to some extent the early 1900s. But I think that this idea is on the move quite a bit. I mean, if you look at the sun, it does appear to have something of a really textured surface to it. It appears to have features, these prominences, these ejections of material, right? And so as we start to actually look at the light of the sun and start to make sense of it, and we're going to do that in just a second, we have to ask ourselves really whether a ball of gas is capable of doing these feats that the sun appears to do, particularly with respect to the kind of radiation that comes off of the sun. And so before we get to that, let's take a little bit more dive into the consensus picture of the sun. So the thing is absolutely enormous, as you may well be aware of. It's about 300,000-ish Earth masses, right? And it's only about 100 Earth diameters across, but it has a great deal of material crammed into that space, which is relatively small. By convention, we say that the sun is about 1 astronomical unit away from us. This is going to become important when we start talking about other star systems in the future, and we're trying to measure our distance to these things. So keep that idea of an astronomical unit in the back of your head, because it's going to crop up over and over again. And an astronomical unit is something like 150 million kilometers away from us, okay? So it's very, very far. The sun rotates at its equator. It takes about 24 days to do so. And so let's start going down into the sun, and let's see if we can make sense of what this thing is. So it has 4 distinct layers to it. It's got this heliosphere, which is this enormous blanket that envelops all the planets and everything else, all the way out to the edge of the solar system. If we come back in towards it, we reach the corona, which is this shining part. You can see it when it's eclipsed like this. You can see the big flowing atmospheric area, which is very, very hot. It's about 10 times the temperature of the next layer, which is called the photosphere. Yes?
Could you repeat what the heliosphere was?
The heliosphere, we'll do it in depth in a little bit here, but the heliosphere is essentially this giant bath of ejecta from the sun. It's this very ionized, very, let's say, atomized pieces of the sun that have flown off. And it has a kind of magnetic character to it. And I know we haven't done magnets yet, but we will. And it causes it to fold back in on itself. And the effect is that it makes a sort of shell for the whole solar system. So that's called the heliosphere. It's essentially the outer limits of our sun's influence, material influence, right? There may be gravitational effects, but in terms of, it's kind of, if you think about the sun as something like a fire hose spraying in all directions, this is not unreasonable. It's kicking off material in all directions, and it's pushing back at some limit at the outer edge, way beyond the planets, way, way beyond everything. Almost, let's say nearly a light year away. Very far, very, very far, basically butting up against the next solar system. There's a big, there's almost a surface, you can think of it, where it's butting up against all of the interstellar material, all of the other stars and so forth. And that is the heliosphere. We'll talk about it with sort of luxury of detail in a moment here. Okay, so as we go down through the atmosphere, which we call the corona, we'll eventually get to this, there's a sort of transition region where there's all sorts of interesting little features that we'll talk about, but then you hit the chromosphere. And then right below that is the effective surface of the sun, the photosphere, and so forth. Now, the chromosphere, well, we'll get to that in a second. All right. Oh, here you go. This is kind of a good picture of the heliosphere. So you can see it's kind of butting up against the outer limits. Now you got to think about our solar system is actually making its own course through the galaxy. This is quite interesting. So, for most of since we even had the idea that there was a solar system proper, right? So this is more stuff from last semester, but generally, for most of human history, we thought of the stars as kind of rotating over our heads every night. The Earth was at the center of the universe. This is perfectly logical because it kind of looks that way, right? It's a very empirically accurate way of looking at things. But once people developed the idea and really agreed on the idea that the sun was at the center of things, they stuck with that very, let's say, conservatively for a long time. And they didn't really consider that the solar system itself had motion within the galaxy. And it does, in fact. So you can think of the galaxy as this sort of pinwheel spiral thing. And the sun is sort of transitioning between different arms of the galaxy as it goes around. And as it does so, it's kind of pushing against everything that's in the way. And so it has this sheath, right? It has this almost comet-like appearance to it. And that's the heliosphere for you. As that material flies out from the sun, it forms this current sheet, which is a sort of rippled layer of this ionized material. And this ends up swirling back on itself to form that heliosphere. So, and it's very much, because these particles are charged, right? Whenever we have charges in motion, we can generate magnetism, and I'll explain the mechanism for that in a moment. But you can imagine that there's a fair amount of magnetic activity, and this allows us to actually even be able to see what's happening here because, yes?
You mentioned ionized. What's the difference between ionized and non-ionized?
Yeah, great question. So ionization is a really interesting concept. In chemistry, the way that they think about it, they're very much accountants in chemistry, and they talk about losing electrons and gaining electrons and so forth. I think that a more material perspective would be something like once a gas obtains the ability to conduct electricity, we think of it as ionized. Now, how it does that requires us to think a little bit more about what electricity is. So the way that the chemists would generally talk about electricity is the flow of electrons. But it's a little bit, there's problems with that, right? When we actually think about what is an electron, for instance, right? We get into some murky waters. And so I think that it's probably more reasonable to think that atoms have an outer surface, which is called the electron shell. And that the motion of that actual surface, when it's in contact with other atoms, allows the motion to be propagated from one atom to the next. So it's something that the outer shell is doing. There's a particular motion to it. We could talk about that motion. It's a kind of peculiar motion called spin 1/2, but we'll get into the weeds very quickly. But essentially what's happening is there's a particular rotatory, involuting maybe motion that's actually being transmitted from one atom to the next. So how do gases all of a sudden, it makes sense in a wire, right? You have all of these atoms, they're literally bonded to each other, and they're in contact with each other. So it makes sense you could transmit motion in a wire. But in a gas, something else must be happening, right? In a gas, we have to start thinking about those shells, right? Usually, what's interesting about ionization is that it happens in a vacuum. So there's no pressure on the outside of these atoms. Their shells can potentially expand quite a bit. In fact, you can conduct electricity in a vacuum with as few as a single atom every, cubic centimeter or something like that, right? That's a huge atom if you think about it. So one way to think about it is that its shell is just, it's lacking that pressure that it would have, say, on Earth or in a gravitational system. It's sort of expanded, right? And those atoms are able to be in contact in that manner. And so essentially, the atoms are sharing the surface motion of their shells during these conductive processes. And that's the way that I think about ionization. So this will keep coming up the more that we understand, the more that we get a material picture for what these atoms are doing. I won't get completely derailed on that. We'll talk about electricity and magnetism more and more. They're at the heart of everything, really. And they're at the heart of light, too, because light turns out to be the way that atoms at a great distance can convey electric and magnetic action to one another. And it turns out that really, when I'm talking about the motion of the shells of the atoms, well, electricity and magnetism are just two ways of thinking about that motion, right? You're talking about the equatorial motion of those shells with magnetism, and you're talking about the orientation of their poles when you're talking about electrical action. Light is the way that atoms convey that. Light is a conversation between atoms. And so this is really important because what happens when we look at the sun or we look at any star is we just get one light signal. But we actually have to split it up into its component pieces to see all the different motions that those atoms are doing. You know, some atoms will be doing different motions than others. The stars are mostly made out of hydrogen and helium. At least our sun is mostly hydrogen and helium, but it's got a lot of other little things in there too. It's got a few heavy elements and so forth. And the way we see those is those atoms wiggle in different ways. And they're light, therefore, the vibrations that propagate out to the atoms in our telescope, those also are going to reflect those different motions. And so we have to break apart the light in order to make sense of it. Now, the first thing that you need to know about the light from the stars is that there's two basic bins for the kind of light that we're going to be seeing. So you see in this picture here a rainbow, right? Sorry, it's gotten extremely warm up here. There's a rainbow and there's a bunch of lines over top of it. And that's for good reason. So how do you actually make light that's like a rainbow? Well, there's only one way we know how to do that on Earth. And the way that you do that is you heat something up really hot. And I mean something that's solid or liquid. You have to heat it really hot. And then if you take your prism, or say you spray a water hose or whatever you want, you'll see a nice rainbow appear, right? You have essentially a spectrum of colors in every possible conceivable color, which is sort of centered. It has a peak to it, right? There's a color that's most obvious. So if you heat up, let's say, I don't know, an iron or something, or let's say a stovetop. That's probably more familiar. So you heat up a stovetop. It starts to glow kind of red, right? So it has this orange red. Maybe the hotter it gets yellow. If you heat the thing hot enough, it'll actually get blue, right? But it has a particular peak to that spectrum, all right? These spectra are called black body spectra. And they're called that because these people were essentially doing these studies in soot-covered chambers. They called black body chambers, and they were examining the output spectra. Now, why does this matter? It matters because there's a different kind of light as well. And it's the kind of light that we're getting from these sort of atrocious overhead lamps right now. It's gas light, right? Now, gases are very, yes?
I'm a little confused
Yes.
As to what a black body spectra is.
Black body spectra is just the different colors of light that are characteristic of heated bodies. So solids, liquids, when you heat them up, you get this particular distribution. I don't know if I have a slide for that yet, but we'll get to it. But, you know, I guess I can draw something for you. If you think about the intensity over here on the y-axis, and you think about the wavelengths over here, you're going to have a peak. So maybe you have, reds over here. This is like the visible range. And you have blues down here. But you're going to have a peak. And depending on the temperature, that peak's going to shift, right? So as it gets hotter, it's going to move towards the blues and so forth, and so on. Yeah. So that's one type of light. The other type of light is gas light. So when you electrically excite atoms of gas, they actually can only vibrate in a few discrete ways, which is really interesting. And it makes sense. If you take a sphere and you try to vibrate it, it can really only deform along a couple of axes in a symmetrical way. And really, light is giving us a readout of how atoms are undulating. That's the best way to think about it. So as single atoms, gases are, of course, just individual atoms. They're not connected to one another. As they vibrate, they can only do so in a few different ways. The result of that is that if we took a prism right now, does anybody have a prism in their pocket? You could use a CD also. It will also split it for you, the back of a CD. Anyways, if we were to split this light that's coming down on us right now, what would be very apparent is that there's only 3 colors coming out of this light. There would be 3 bands. You'll see a green one, a blue one, and a red one. But if we had some of those old-fashioned incandescent light bulbs, maybe you have some at home, those are actually heated wires. And if we took that same prism and held it up, we would see that rainbow. So there's two basic ways that we get light, and they're from heating things, and they're from exciting gaseous atoms electrically, which is what we have in these things. So when we look at the sun, what's interesting is that, okay, I guess one more principle is necessary to make sense of this. If a body can, this is true for black bodies or for gases. If it can emit a particular color, like the lights up here, this red, blue, green, if it can emit that, it can also absorb that. So if I was to heat up, if I turn this off, this lamp off, but the gas is still in there, and I put a heated incandescent light bulb behind that, it will actually absorb those same colors. The atoms will absorb that energy, and they will take it up. Now, they may or may not re-emit it, but they're going to absorb it, definitely. So when we look at the spectrum from the sun, this is essentially what a prism would show you from the sun if you had a really nice prism, is that there's lines in the atmosphere. So these overlaid black lines are those different atoms, those gaseous atoms that are in the atmosphere that are sopping up the black body radiation from the surface of the sun. So the peculiar thing about this, and this is where I think things are really on the move today with respect to the sun, is that for most of the last 100 years, we've treated the sun as a burning ball of gas. Now, in recent times, the people have begun referring to the sun as a ball of plasma instead, and I think there's good reason for that, although your textbook still calls it gaseous plasma. Now, the sort of interesting moment in science right now is that no one's ever been able to make a rainbow appear from a ball of gaseous plasma in a laboratory on Earth before. Of course, gases always give us these line spectra when we look at them on Earth, no matter what. There's nothing you can do about it. Now, you can put the gases under a lot of pressure, and you can broaden those lines so they become a little hazier and thicker, but you never, ever get this kind of a black body spectrum from a gas. And so you might think this is just arbitrary, but it's not arbitrary, because if we don't understand the sun for what it actually is in terms of its material structure, then we might be making mistakes about how we interpret the lives and deaths of stars, which is going to be a huge part of our story as we work towards cosmology. So the sun definitely has this black body spectrum. It's almost a perfect black body. In fact, it's the most perfect black body we've ever seen. But it has this overlaid atmosphere, for sure, of all of these little lines upon it, too. So we have a gaseous atmosphere, and we have something else which is giving us a black body. Now, the argument for how it is that a ball of gas could give a black body, theoretically, was developed by this guy named Arthur Eddington back in the 1920s. And Eddington came up with this mechanism, which is essentially under the body of work called radiative transfer. And the idea is that these photons, these really high energy photons, are emitted at the center of the sun during these fusion reactions. And they take millions of years bouncing around inside the sun. And as they bounce around for millions of years, they downshift in their frequency. They lose energy. And then by the time they get to the surface of the sun, they're essentially magically in all the right frequency domains to give us this black body spectrum. Seriously, that is the standard model for how the sun generates this black body, which is a really, really, really fascinating moment, because I think that proposal has lost its steam recently. I think that it's becoming more and more difficult for scientists to accept that that's a reasonable approach. You know, if we were able to, in a laboratory, actually take gases, compress them, and generate anything even remotely approximating a rainbow, then it might have some legs to stand on, but no one can do that. No one has ever done that before. And so this makes it a really, really, really interesting piece of the whole puzzle, because, look, we're in the first class today, and we're talking about the material basis of the sun, but all of the things downstream from today are built on the idea that the sun is a ball of gas. Now, if the sun isn't a ball of gas, if it's something more metallic, more like condensed matter, right? More like liquid-like, right? That makes a very different picture for the way that stars evolve and live and die and how they're born in the first place than something like a ball of gas collapsing on itself. So this is really, really hot. It's really hot, controversial, interesting stuff right now. And my goal is not necessarily to take a stand on this, but I do want to expose you to the interesting pieces of the puzzle that are unfolding. So here you go. We're looking at the atmosphere, right? So if you pull all those lines off, and you can do this in a laboratory on Earth, by the way. You can take mercury, you can put some current through one of these bulbs, right? You're essentially making these fluorescent bulbs out of these different elements. And you can see that each one of these elements appears in the atmosphere of the sun. Those are the lines that were blotted out over top of the continuous rainbow. And this is easy to replicate. This is fairly solid and compelling as far as I can tell. So these lines are called the Fraunhofer lines. It's interesting. Most of this was really developed by these two guys. There's two characters. This guy named, yes?
How do you spell Fraunhofer?
Oh my goodness. Fraunhofer. Yeah, it's in your textbook too. They'll tell this story as well. So there's this guy named Bunsen. You guys probably know Bunsen burners, right? Back from high school or something. Bunsen was working, basically developed this entire idea that you could burn these elements or excite them electrically, and you could get these distinct lines out of it. Pretty much single-handedly developed that spectroscopic science by himself. His buddy Kirchhoff, there's another guy named Kirchhoff, was doing all of the black body science, and he was basically deducing how you could analyze a heated body to determine its temperature just from the spectrum as it moved around. And I don't have time to deduce all of that for you right now, but the basic idea is that depending on where this peak shifts, right, depending on the temperature profile, depending on the light that you get out of it, you can tell the temperature of it. This is how we know the temperature of the sun, right? Because we can look at that photosphere, that surface, and we can get the black body temperature of it, which gives us the temperature. Okay, so these two gentlemen put this all together. This was back in the late 1800s. And, they found that basically the sun contains everything we have here on Earth, but just in different proportions. So something like 73% of the sun's mass is hydrogen, which is the simplest element. It's the simplest atom. It has just a single electron shell to it and a single proton nucleus. Most of the universe is still comprised of hydrogen, which is interesting. And then the other 25% is the next simplest atom, which is helium. And we'll talk about, there's all these other atoms that appear, the things that we love, like that, we couldn't live without, we're made out of, carbon, oxygen, nitrogen. That's only 2% of the star. And we'll talk about how those elements are made, because we believe they're made inside of stars, actually. And the process by which that's done is through fusion, and we're going to go through in this course and talk about fusion. And it's going to get a little bit technical, but it might be fun because I think that it's important that we understand why. Because fusion might save the whole world one day, right? Fusion's an incredible promise. If we can find a way to actually do fusion reactions here on Earth, we're talking about beautiful, clean, safe, endless, abundant energy. And of course, everything that we depend on in our world depends on having power. And fusion's actually quite promising. However, the approaches to fusion research right now are entirely based on this gaseous model of the sun. This is another reason why this is not an insignificant oversight. If this is a paradigm which is shifting in astrophysics under our feet, like we might be witnessing a true revolution on the order of Darwin coming up with evolution, right? Or Copernicus saying that the Earth is not at the center of the universe. Something like that may be happening right now in astrophysical sciences with respect to the composition of the sun. And the reason it matters is because of fusion power. Because if we're trying to build these fusion reactors using gaseous plasma, and it's not working, and just so you know, it's not working, right? Well, what if our approach is sort of wrong? So there's a small team at NASA that published a few papers where they were able to actually take a solid lattice and essentially squish some smaller atoms in between the layers of the lattice. And what they did was they applied like a little bit of pressure to the outside, not a lot. They applied a little bit of pressure to the outside of this lattice, outside of this package of atoms, right? And they were able to fuse those smaller atoms by squishing them like that. And this was done at essentially ambient room temperatures. It wasn't this super high energy, expensive reaction, right? Now, one of the most difficult parts about the approach that people are taking to fusion today is that they have to control this ball of plasma. They're trying to use magnets to hold this, basically an artificial, what they hope is an artificial sun in place while they squish the atoms together and hope they'll join together. And when the atoms join, they fuse and release a little bit of energy, and we can hopefully pick that up and do work with it. But it's not really tenable. It's not working out, right? You know, they've been able to fuse things for sure, but the cost of maintaining that magnetic infrastructure of holding that gas in place while doing this, it costs 400 or 500 times the amount of energy that they get out of the reaction, right? So maybe the approach is misled based on our misunderstanding of the stars. This is not out of the question. I think that it's actually really promising that these new ideas are coming to light. So there we have it. That's the sun. It's hydrogen. It's helium, and some of that helium is actually being produced inside the sun. We'll talk about that later when we get to fusion. And this whole story of stars has real relevance to our lives because it's going to determine whether or not, really, I mean, it's hard to overstate the importance of energy in terms of the material economics of it. You know, everything that we do in our lives really comes down to paying for fuel. Even growing food, right? It's very energy intensive. Transporting ourselves, all of these things. You know, if we could actually harness the power of the stars here on Earth, we would be in a very, very different civilization than we are today. Quite a beautiful one, I believe. All right, so this is the standard model for the sun, which has basically all of this, all of the reactions happening deep inside of it, and essentially being conveyed outward to the surface, as I was mentioning. This interior is thought to be, of course, entirely gaseous, and there's these convective zones which lead to the surface features. So do you guys know what convection is? This is probably something to establish right now. Anybody? Convection. You heard that before? Convection oven? Yeah. So convection is really just this war between density and well, it's really just a density business. But what happens is when things heat up, they occupy more space, right? And so they become less dense and they rise. So if I was to bubble. If I was going to heat something on a stove, right, as the molecules started getting heated up, that means they're moving around more chaotically. They're going to start taking up more space, and they're going to be displaced by the cooler things, which are going to sink down. And so under our feet on our planet and beneath the surface of the sun, this same process is happening where the heated things are rising up, the cooler things are falling down, and you get these little cells of turbulence that develop. Well, they're not quite turbulent, they're quite patterned actually, but you get these rolls going on. And this is thought to explain some of the granulation patterns that we'll see here in a moment on the surface of the sun. No doubt they are playing a role, but the actual details of that are a little bit up for grabs still. One thing that's really interesting regarding this idea is that the sun has this apparent surface to it, right? Now, the fact that the sun has a surface is an interesting argument against the sun being made out of gas in the first place, because it's not clear that gases should, if you look at the basic ideal gas laws for how gases should behave, they actually tend to spread out and they tend to thin out and so forth. And so oftentimes astrophysicists will talk about the surface of the sun, and definitely there's a density gradient where it goes from basically being a rarefied atmosphere to having the density approximating water at the surface, on that order at least. It's getting very, very dense. And I was talking to Nikki Fox, who's NASA's Parker Solar Probe director. So they sent this probe out to the sun for the first time. It didn't go all the way to the sun, but it kind of tasted the outer atmosphere. And I was really trying to press her on what do you mean by surface exactly, how does this thing have a surface? Does it have a surface to it? And it seems like it does definitely have a surface to it. And so if it has a surface and it has a density which is approaching the liquid-like domain, then do we have a true phase transition at the surface? Does it actually have a real material like boundary to it, where you actually have some sort of condensed phase of material that's not gaseous? I don't know, and I don't think that I don't know how to look at it any other way, but it certainly becomes extremely dense right there at the photosphere, and so what else can we say about it? So the photosphere, by its black body readout, is about 5,800 Kelvin, which isn't that hot, actually. So by contrast, oh goodness, I don't have the number here. The actual atmosphere is something like 10 times as hot as that, which is very bizarre. This is sort of like having an oven where you stick your hand inside and it burns your hand, but you can touch the wall and you're just fine. Like it boggles the mind to imagine how this could happen to begin with. Now, it may be that there's some confounding factors there regarding why we think that there's this disparity in temperature. So the black body temperature, black bodies were developed with these ideal, solid, soot-covered chambers, right? Now, liquids can also give us a black body spectrum too, but the problem with liquids is that the temperature we get from a liquid is not an accurate temperature with the black body. The reason for that is because liquids move around a little bit. They dissipate a lot of their heat into frictions as they move around. And so the temperature that you'll get from the color of a black body from a liquid is going to be effectively cooler than it actually is, right? So some of that, the thing is actually perhaps hotter than it looks because some of that heat is being dissipated in a way that inside of like a solid lattice like this table, it can't really move around, right? The temperature can't be lost to those kind of frictions. And so this disparity in temperatures is something we'll revisit over and over again. All right. Oh, great. I did bring in the black body. So here you go. This is actually a much better illustration of the black body than the one I tried to draw on the board. What you can see is that for these different curves, so you have a 2,000 K curve, a 3,000 K curve, 4,000, 5,000. And what you can see is it shifts towards the blue the hotter it gets. The one that we get from the sun is, of course, listed there, this beautiful 5,000 K spectra. Now, it's somewhat miraculous, but I suppose that it makes a lot of sense. The peak of the solar output is this visible light, right? And of course, that's what we use to see here on Earth, which is no coincidence, I'm sure, right? Because our eyes are tuned exactly to our star. Those are the colors that we see. Maybe if we'd come from a different planet with a different temperature, we would see slightly different frequencies. Maybe they would look the same, but we would be seeing different wavelengths, right? Because the peak would be slightly different for a different temperature star. So another remarkable piece of the puzzle is that our atmosphere is actually really, really opaque to most electromagnetic radiation. Most light can't get through our atmosphere. The only light that can get through our atmosphere is a tiny little window in this exact same range. That's because water, nitrogen, methane, all the various things in our atmosphere absorb the light at all of those other frequencies. There's a little window in the radio frequency band as well, which is why we can do radio telescopes here on Earth. So it's kind of this incredible tuning, right? You know, we talked a lot last semester about how lucky we are to be, well, I don't know if lucky is the right word, but it's very rare that a planet would be in this particularly amazing location, right, where it's not so cold that all of our water is frozen over, so we can actually move around, our cells can function and flow. It's not so hot that our atmosphere is getting cooked off. We've seen that happening a lot in a lot of these exoplanets that have been discovered lately. And then what's even more remarkable is we have this incredible little window in our atmosphere where we can get light from the sun. That's by no means guaranteed whatsoever either. So the tuning between these two is just kind of incredible. Now, when we zoom in, we've gotten very good at looking at the surface of the sun. We start to see it has an actual texture to it, which is quite incredible. It actually we can see ripples on the surface of the sun, but these granules are quite interesting. These things are huge, by the way, so each one of these little granules that you see is something like 1,000 kilometers across, something like the size of Texas. The dark regions are cooler, and the bright regions are warmer. And the basic consensus idea is that as those convection cells that I was talking about, those little upwellings and downdrafts, they swirl up and they sort of make they push up, and each one of these represents the tip of a convection cell, something like that. And you can see this on a boiling pot of water if you've ever, you put some, if you've ever gotten something making some soup or something, you can actually see these little cells appear where there's individual little granules on top. Has anybody seen this before? You get the little bubbles will appear, and you get these almost little pockets. They're not so different than these. They're sort of static structures that persist over time as you're boiling your dinner. So, each one of these granules lasts for only about 5 or 10 minutes, but they do persist over those orders, and that's probably the same as the pot on your stove. All right. The chromosphere. So the atmosphere that's right above the photosphere, so right above the surface of the sun, in so much as it has a surface. Yes?
I have a question
Yes.
about the granules, and you said, so do you mean that they last 5 to 10 minutes in their one area before shifting again, kind of like a boiling pot?
Yeah, exactly.
Got it.
Yeah, so the next time that you're cooking something, take a look at take a look at how long the patterns persist on the stovetop. I think they last on a similar order. Maybe smaller, since it's a smaller surface, it's not as hot. There's not as much gravity. Probably quicker, yeah. But you do sometimes get these stable patterns. I think inside of liquids on a stovetop, they're called Bernard cells, actually. You can check it out. So yeah, these are not long lasting. So right above that, either whether it's an effective surface or whether it's a true surface, jury's still out, we have this thing called the chromosphere. This is a sort of transition region where this material, in one state at the surface is sort of persisting up into the atmosphere. And you get these really cool little whiskers. We call them spicules. This is not the best picture. Here's a nice high contrast image of them. There's actually these little whiskers that go up. And those whiskers are really interesting chemically, right? Because they seem to imply complex molecules are actually interacting inside of these things. So they're true structures in some sense. They also persist on the same order from what I recall. So features begin to appear at that point. Now again, looking at the temperature map here, this is of course we can imagine the inside of the sun. One second. The inside of the sun and the outside of the sun. So over here is the atmosphere. Over here is the surface of the sun with the photosphere. And you can see the temperature is much higher in the corona than it is at the surface of the sun.
I just had a question.
Yeah.
The spicules, are they created by the chromosphere, or are they kind of separate to it in some way, or not separate?
I think that in some sense, they have black body characteristics like the photosphere. They're really, really poorly understood, in all honesty. The idea is in some sense that you have, and we'll talk about this when we get into magnetism, the surface of the sun is in some sense patterned by, this is very conductive material, right? And so these magnetic fields appear, and the magnetic fields organize the material, and it's sort of this feedback loop. And the spicules seem to be a result of the magnetism interacting with the conductive surface material of the sun, that hydrogen, helium, whatever it is, which is electrical, and it's conducting, and it's getting kind of twisted around and pulled up and yanked out. There's really two big forces at play at the surface. Well, there's three. You have this magnetism and electricity, which is really, really important, but probably the least understood. You also have gravity, which wants to pull everything back down, right? So all atoms pull on one another for whatever reason. We can talk about the reason why they might do that. But the atoms are all pulling on each other, especially when there's a lot of them in one place. They're pulling really hard. But There's also this almost evaporative phenomena where the atoms break loose, right? There's a lot of pressure from the inside. There's radiation pressure. Light actually pushes. And so as these magnetic arcs kind of break open sometimes, they become unstable. They fling pieces of material out. And there's this constant combat between gravity holding everything in and things being kind of slingshotted out by the magnetism and the radiation pressure. And that's how we get solar wind, which we'll get into the details of that soon enough. I do want to, again, point out how bizarre this is and how this may actually, in some sense, be a serious point where the theory is going to develop in the next century or in the next 10 years or wherever. So the way that we understand it right now is that the corona is extremely hot, on the order of millions of Kelvin, right? I think 10 million Kelvin, something like that, compared to the photosphere, which is only 5,000 Kelvin. Now, this seems really bizarre, but the concept of temperature, which seems so mundane and prosaic to us in our everyday lives, it starts to break down when you get into really rarefied conditions. So what is temperature? It's just the average kinetic energy, let's say the average motion of the atoms in a system. So if I heat up this table, all the atoms are going to start jiggling, essentially. If I heat them up too much, it's going to combust because it's going to react with the oxygen and start a fire, and that won't be any good. But what happens if I have only one atom in this whole room and I heat it up? I give it a lot of energy. Well, if you walked into this room with that one atom, would it feel hot to you even if that atom was at 1,000,000 degrees? Probably not. So the corona is sort of like that one atom in the room situation, where it's so rare. There's very few atoms at the corona, especially the further you get away from the sun. But they're moving really, really fast. And so their average kinetic energy is really high. Their temperature, technically, is really, really high. But it doesn't necessarily mean that the place is that hot. And this sort of dawned on me when I was talking to Nikki Fox about this, because she was talking about how they were flying their probe into the corona, and it was millions of degrees. And I'm like, how the heck do you fly a spaceship into this 1,000,000-degree region of the sun? And so she slowly starts kind of explaining how it, this concept of temperature actually kind of breaks down in those conditions, right? Because when we think about temperature, we think about effective heat that you can communicate, right? When we heat up an oven to a particular temperature because we want to cook our food, right? So, it wouldn't do me any good to heat up a single atom inside of my oven and try to cook my dinner with it. I'd be there for 1,000,000 years trying to get it done, right? And so we have to be really careful with this concept of temperature, because as crazy as it seems that the atmosphere would be much hotter than the surface of the sun, it's not quite the right way to think about it. I don't think that hotter is the right way to think about it, although the average kinetic energy of those particles is really high because they're being accelerated off of the sun really, really fast as those magnetic loops break, and it flings things out. And of course, the radiation pressure is driving all of this and so forth. So we have to think about temperature in a little bit of a different way. All right, and this is a picture from an eclipse. Guys, we have a total solar eclipse this year. Big year. I highly recommend it. I don't think it's coming through Oregon, but if you can get a road trip together, it's happening in April, I think between quarters for you guys. So we're gonna be going down to Austin to see it. I would highly recommend it. If you've never seen a total eclipse, it's a pretty sublime, profound experience. The bugs come out and the birds stop chirping. Yep. I think it's coming up through Mexico, through Austin, across the Midwest, and up to upstate New York. Yeah, so you're gonna have to drive quite a bit to get there. Yeah.
Have we had one of those in the last 10 years or so?
There was.
I remember one happening.
It wasn't there was. I haven't lived in Oregon for that long. There was one out here, I think, maybe 5 or 6 years ago.
Yeah, it was California.
Yeah, through California. And I think there was a partial one last year that maybe you guys saw it down here, right? Yeah, I live up in Grants Pass. Yeah, I couldn't see it. It was cloudy that day. I was so bummed out. which is the other reason we're driving out to the desert in Texas to see it, because there won't be any clouds. Best place, best chances anyways.
I just remember there being like a big event and everyone buying those like little solar glasses.
Yep, that's going to happen. You can also, we're going to try to project it with our telescope onto a wall too, so you can see it, which should be cool. We're going to do a little live event for our podcast out there. So that's going to be pretty cool. I will keep trumping that up as it comes. I think it's April 8th is the day of the eclipse. At some point in your life, you need to see one of these. They're really, really profound. When I was, I think, a kid, I saw one, but I have yet to see a total solar eclipse, and I'm very excited. But it's important too because actually, for science, this is the only time historically when people could see the corona, and so there's been a number of really cool experiments that have gone on to make sense of the sun. Some of the first tests of general relativity, which we'll deal with later, involved a total eclipse of the sun because they were actually able to see the position of the stars right next to the sun, which they're never able to do. And the general idea today is that large bodies can bend light gravitationally, which is pretty far out. It was brand new at the time, and the way that they proved that idea was by actually taking pictures of stars right next to the sun during an eclipse and seeing how they moved when the sun was right in front of them, which is pretty cool. Okay, so the corona is enormous. The atmosphere essentially extends, I don't know, it depends where you draw your lines, but definitely past the Earth itself. Technically, this helio sheath is all really composed of stellar material that's being flung out into space. And of course, the magnetic field of the sun itself is pulling that back around, and it makes a sort of croissant, right? Some sort of envelope that pulls it all back together. All right. So these particles that are flying out, they're really fast. They're going at something like 1,000,000 miles an hour. And this is, of course, part of why we think that why we would say the temperature is so high in the corona. It's quite interesting. So these particles get kind of, as they're emitted from, as they're swirling around at the surface of the sun, they're being accelerated by these magnets, right? There's magnetic fields developing, and I'll start the next lecture with explaining magnets to you guys, but just let's assume that there's this magic force called magnetism, which won't be magical soon, but let's just accept it for now. That's capable of accelerating these charged atoms as they move around on the surface, and they get going really fast on the surface, right? And occasionally, those structures, just like the convection cells, they're unstable, right? They're not solid like a table. They're in some sense fluid. I think fluid's a reasonable word to use. Fluids really just talk about flowing materials, so gases, liquids, whatever. So there's this very structured fluid. The fluid is accelerating these atoms, these particles, and they break apart sometimes. And when they break apart, they go flying like a slingshot off the surface of the sun at incredible speeds. What's really, really interesting is that those particles actually speed up as they get further and further away from the sun. Now, this is a really interesting mystery that I don't know that anyone has totally made sense of at this point. But the best explanation I've heard is something like they have a certain amount of forward momentum to them. Things that are in motion tend to stay in motion. They have that momentum, but they're restrained by the gravity of the sun when they're close to it. When they're further away from the sun, the gravity is not holding them back as much, and their forward momentum takes over. But it's very bizarre. So the solar wind actually accelerates. Now, let's see here. There's these things we call coronal holes. You see this big area down here, right? And these ones have enormous loops of magnetic fields that reach out into space and all around them, right? They're very patterned, consolidated magnetic fields. And when these loops collapse, they have the potential of actually flinging big chunks of the solar surface out towards the planets and towards us. This is what's called a coronal mass ejection. And these things can be potentially quite devastating to life here on Earth. At least to electronic life, right? And we're a very electronic civilization. So think about the last time this happened was called the Carrington event. This was right after the birth of telegraphs. And it destroyed all the telegraph communication all around the world when this happened. There was this big, huge solar flare that just smashed right into the Earth. Auroras, right? Has anyone ever seen an aurora before? They're usually only seen at the poles. This is where our own Earth's magnetic field fails to shield us, essentially, from the solar wind. But those coronas reached all the way down into America at that point, all the way down into Europe. You could see at the time, this was in the 1800s, you could see these coronas during the daytime, right? Because as this huge coronal mass ejection smashed into the Earth. Now, we've had coronal mass ejections since then, but none of them have been such a direct hit as they were during this Carrington event. So this is a serious concern, and trying to predict these and map these is an arduous process, and I don't think that, we have some lead time. It takes a little while for that material to get to us, but not a lot of time. And so, I was talking with another lady at NASA who's looking at the Space Weather Initiative, and one of the plans that they're trying to come up with what to do is how to actually power down different parts of the grid in anticipation of one of these coronal mass injections. So, the only hope right now, all of our power systems are coupled to everybody else's power systems all throughout the country. And the thought is that if somebody gets hit with the coronal mass ejection on one side of the globe, the problem is everybody is essentially going to be affected by it. So how do you insulate each one of those from each other? How can you power them down so that you save your computers and keep everything safe? I mean, man, it occurs to me whenever I start looking at ancient history, we have all of these rocks, these huge megaliths from Mesoamerica to ancient Turkey, and we can learn about the peoples of those ancient worlds. But if you think about us, like, where is all of our knowledge stored at, right? It isn't written on rocks, I'll tell you that much, right? It's inside of ones and zeros. It's very ethereal. And we, it's been a great boon for our civilization to have all of this fantastic digital technology and fantastic access. I can pull up the whole world's knowledge base from Wikipedia on my phone, right? But it's very, very fragile at the same time, right? And it's particularly fragile to electrical disturbances. And so this is, last semester we talked about the risk of comets and asteroid strikes, which is serious. But and it's serious from an existential threat because it could kill a lot of animals, right, including ourselves. It would wipe out a lot of people. And NASA's doing a great job of tracking all those asteroids. We talked about that. But our knowledge base, right, our immaterial knowledge, our immaterial wealth, all of our transactions and economy, it all exists inside of ones and zeros, which are very much susceptible to the whims and the moods of the sun. So let's pause here for today. Oh, you had a question. Sorry.
I did.
Would a solar flare affect hard drive?
Yes, that's exactly what I'm saying.
Yeah.
Yes, bad news. So let's start there with space weather next time. Again, please contemplate whether you want to keep doing this for 8 weeks. And hopefully I'll see you guys back here on Thursday.